Nice, nice try.
I took those 5 off topic questions.
All right.
Sorry, I'm
All right. I think I forgot the top hat last week. I forget. So there's one.
My phone died.
There's two. 10, 9, 8, 7, 6, 5, 4. All right. Somebody did it. 3.
My phone died.
There we go. 10, 9, 8, 7, 6, 5. You gotta be like, there we go. Okay. There we go. Now we've top added. So what actually matters, of course, is this. So there you go. Let me begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, I thank you for these students. Just ask you to bless our work today, Lord. Help us to glorify you and what we do. In your name I pray, Lord Jesus. Amen. All right, so today I'm into my chapter 3, right? Which is on what? It is on topology and limits. So, what is topology? Well, topology is the study of open sets, or if you like, it's the study of continuity in the abstract sense. Now, in here, we're talking about the complex plane primarily. So, the topology we'll describe is basically based on this guy right here. So, dr of z naught, what that's going to be is z and z naught, rather z in the complex number system, such that the modulus of z minus z naught is less than r. In words, this is the so-called open disk with radius r centered where? At z naught, right? So if you look at the definition here, we're just taking the collection of z which are at most distance r away from z naught. So if I were to draw a picture of this thing, right? It's kind of boring. Here's your z naught, right? And then you got your radial distance away from there, whatever that is, r. Now r has to be what? It probably should be positive here, right? Otherwise, kind of awkward. So positive r like that, and then you got yourself this, all these points in here. That's an open disk centered at z naught with radius r. All right? First definition. So a second definition, and we have like so many definitions today, just so many. Definition 2. S, a subset of the complex plane, all right? And then if z naught is an element of S for which there exists r greater than 0 such that the disk of radius r centered at z naught is a subset of S, all right? In other words, if this disk is a subset of S, then z naught is an interior point. It's an interior point. All right? Definition. If each point in S, some subset of the complex numbers, is an interior point, then S is open. Or we could say S is an open set. All right? Now, let me, yep.
Do we have to clarify that it's an interior point of S, or do we just say it's an interior point?
Of S, yeah. Each point in S is an interior point. Oh, fine. Yeah, I got your point. Of S. Thank you. Sure. Although I guess that begs the question, what else could it possibly mean? But fair enough. Yeah. But then again, you just took topology, so you might have an idea. Anyway. Okay, so yeah, you could spend a whole class just talking about this, right? Like Dr. Sprano has taught a course in topology like the last 2 or 3 years. I keep getting sucked into teaching it too, wherever I've been. Students need to know it. It really should be part of the required curriculum, but it is mighty hard to change course structures these days. So it's kind of frozen in place what we have. Anyway, all right, so you can also, let's look at an example. And in the example, I'll introduce some other things. Okay, so like, I'm going to draw a dotted line, and then I'm going to draw a solid line to be included. All right. So here is a set S. All right. And I'm going to use color coding. So S is like everything inside here. All right. I would shade it, but you know, stupid whiteboard. But let's say S also has some points like out here. Like this is also part of S, all right? Right? Great. So where are the interior points of S? Right, so like for example, let me just give you an example. This point would be interior. Why? Because I can draw a little disk like this, and it's completely a subset of S, right? That makes it an interior point. Okay? On the other hand, this point out here, let me call it Z1. Z1 is not an interior point, right? Z1 has got what? If you look at this, so like Z1 is the only point in S inside the disk of, I don't know, let's say this is radius 1, disk of radius 1 centered at Z1, right? So that would make Z1 an example of what's called an exterior point. These are also sometimes called isolated points. A point is exterior or an isolated point if there exists an open disk around the point which only contains the point and nothing else, right? On the other hand, an interior point, you can find there exists an open disk, right? Such that it's a subset of the set you're judging it to be interior, right? And you can also see geometrically that it's clear that any other disk of a smaller radius would also be inside the set, right? If you've got one, you've got an infinite family of them shrinking to radius 0, right? That's all there. How about this point here? Let me call this thing Z2. What's the deal with Z2? If we take any open disk around Z2, I'll just draw it for the sake of us seeing it like that. You see what's going on with that? Well, you've got some points inside S, right? Inside, and what else do you got? Outside, right? Out. That makes Z2 an element of what's called the boundary of S. And so we use the partial symbol in here for boundary. A boundary point is a point for which every open disk around the point contains points inside and outside the set. This is a boundary point, yeah.
Shouldn't we put that point where the line is continuous instead of that? Because...
Oh, no. This is also a boundary point. So,
Do we have a point where the line is not?
but here, this is also a boundary point, Z3. Now, Z2 is not an element of S. A boundary point does not have to be an element of the set. Boundary points can be outside the set. They may also be inside the set in the case of Z3. Like Z3 is an element of the boundary of S, and Z3 would be an element of S. It's both. Yes, sir?
You answered my question.
Oh, okay. Yay. So definition. S. Oh, man. Can somebody move the camera for me?
did, but it's hard to
So if you're going to do that, you gotta accept your fate and move. I see you're eating, so well, actually, this is a good question. Can you eat, do the camera, and take notes at the same time?
Of course.
That would feel like I could write a letter about that. Like when I'm writing about your camera work, I'd be like, not only is he an adequate cameraman, he can eat and do camera work at the same time and take notes.
Would you rather?
That is like, oh no, you can eat. I am not making some sort of passive-aggressive, sarcastic comment about you eating in my class. Not that we're eating inside the room where it says not to eat somewhere, but actually this isn't a physics lab, so you're free to eat here, right? In the physics lab you can eat, you just shouldn't. I don't know. There's some radioactive stuff in there, so I don't know, there's, whatever.
Like bananas?
But you guys, some of you got the jab, so you don't care about these sort of things anyway. But let's see here. Yeah, I worked it in. Let's see here. S has. Man, I've completely derailed myself. So what I was getting to is if the boundary of a set is a subset of the set, all right? If the boundary of S is a subset of S, then S is closed. I personally am not fond of this definition, but it is kind of a nice geometric definition. There's an alternate definition, which I will not prove the logical equivalence of, but you can if you want, which is that if C minus S, all right, which is equal to Z in the complex numbers such that Z is not an element of S, is open, that's true if and only if S is closed. So and this is oftentimes, I find this to be a very convenient way to think about things. It's closed if its complement is open. Let me give you an example. Now, how about this, before I go on? Example 1, is this closed or open? None of the above. See, because it's got points which are not interior. Not every point's interior. There is an interior, like the interior of this set, the collection of all interior points, would just be like take the same shape and make it fuzzy on the edges. And throw out the exterior points. Those are definitely not allowed. All right. So example 2, we might have something like, oh, I don't know. How about a closed disk? So here, this would be D, radius R, centered to Z naught. And this is typically, so this is unfortunate, but it is what it is, guys. So here's Z and Z naught, and Z in complex is such that the modulus of Z minus Z naught is less than or equal to R. This is unfortunate, but it is what it is. The bar here does not speak to complex conjugation. This is the topological operation of closure. So like the closure of a set, closure of S is basically like S union limit points. So I guess that begs the question, what's a limit point, right? S unioned limit points of S. That's what this notation means. So I'm sorry, you need time travel to understand this part, but give me a second, I'll come back and define limit points, all right? But let me finish my example 2 before I do that, okay? So this is the closed disk, right? The edges are not fuzzy, and it's all of this, right? It's like this whole disk. Now, what's the complement? Well, okay, fine. A couple different ways to think. Let's think about it both ways. What's the boundary of this set? What's the boundary of the closed disk? Bleh. Words. I'll get it eventually. Oh man, what am I doing? Partial derivative with respect to R? Like what on earth is that? This is not partial derivatives, this is just topological boundary. All right, so boundary of the closed disk of radius Z naught is equal to what? It's Z in the complex numbers such that z minus z naught is equal to r. Right? So if I can use some color coding for that, it's just this. Right? That's what this is. Just the circle of radius r, right? Those are the boundary points of the disk. Right? So is that a subset of the closed disk? Well, certainly it is, right? So that's a closed set. That's the one way to look at it. The other way to look at it is in terms of its complement. What's the complement of the closed disk of radius r? The open disk and everything else. How about everything except, it's just everything else, right? It's everything out here, right? These points out here, these are the complement. This is C. Take away the disk of radius r centered at z naught. Man, I really should have given that a simpler name. I should have called it like S or U or something. All right, anyway. Why is that an open set? The thing I've just shaded in blue. Well, pick an arbitrary point, right? You pick a point like here. Can you find an open disk that's centered around the point and is not inside the closed disk? You can, right? This proof I'm giving you is a geometric proof. That's not what I would call a rigorous proof, right? Okay? We should look at a rigorous proof of something here because, I think I've asked you to do one in the homework somewhere. I guess before I do that, though, I should probably tell you what a limit point is. What's a limit point? Or maybe some of you can tell me. I have to look it up so I don't mess it up yet.
A limit point of S would be a point. I don't know if it needs to be in S or not, but any open disk you draw around it will contain its S.
That is correct. So correct. Y, an element of C, is a limit point of S if and only if every open disk centered at Y contains points in S other than Y. Yeah, this means that every open disk centered at Y in C contains points inside S minus Y. So what's not a limit point? We have some on the board. See these? Isolated points are not limit points because there's lots of open disks around these points which just contain the point. They don't contain other points in S. But are boundary points limit points? Certainly. Boundary points are limit points. Does a boundary point have to be inside the set? No. Does a limit point have to be inside the set? No. That's good, right? Because we take limits of functions, and if we could only take the limit of a function at a point inside its domain, well, that would hardly be interesting, right? The whole concept of limit is designed so that you can get outside the edge of where algebra makes sense, right? Okay, so let's do a careful proof. Let us consider the set S equal to, z equals to x plus iy, such that the real part of z, which of course is x, right, is greater than 2. I would like to prove to you that that's an open set. All right, that's what we're going to do. Prove it's open. So first of all, before you do any rigorous proof, a good idea is to first do the informal geometric proof. First gain a concept of what you're trying to do, right? Draw a picture of what it is you're trying to prove. What does this thing look like? Let's see here, x greater than 2, right? So this is x equals to 2, right? And we're basically, we're out here, where we're trying to prove that this half plane is an open set. So how do we have to proceed? Well, we have to, pick a point over there and show its interior, right? So if I pick some point like this, right? Let me call it Z naught. I just picked that point. I want to show that that's interior. Well, what could I do? I mean, you can kind of see it in the picture, right? I draw like that, right? Okay, so now that we have the picture, we have some idea, let's just try it out. So let's let Z naught equal to X naught plus IY naught, all right, be an element of S. What do I need to do? I need to find an open disk, right, which is centered around that point, and it's inside the set. So you guys tell me what I should pick for my radius. What's the greediest thing you could pick? 2 minus x naught, right. Notice the real part of z naught is equal to x naught, which is greater than 2. Thus, r is greater than 0, right? That's important. We need to know that the radius is positive. If your radius isn't positive, the rest of your proof is nonsense. Okay? Yeah.
It should be flipped, right?
Oh man, what have I done?
No. X naught minus 2, because X naught is big greater than 2.
Oh, yeah. So what was I just saying? So, yeah. As usual, my comment is wrong because pride goeth before the fall, and it's just like a law. If I make a comment about the logical importance of checking something, I haven't checked it, and I'm an idiot. So it's just like, kind of like my helpful, hurtful video with all of its many errors. I hope we found them all. I'm told that I put a minus in cosine somewhere in that video. There's the formula for cosine doesn't have a minus in the middle. It's e to the I theta plus e to the minus I theta, or if you like, put z there for cosine z, right? There's a plus in cosine, minus in the sine between the things added. Sorry. Anyway, all right, so that would make x naught minus 2 positive, right? Okay. Great. So consider z an element of the disk of radius r of z naught. We need to show what? If I want to show that this, I want to show that the disk of radius r centered at z naught is a what? Is a subset of S. That's what it takes to prove that this is indeed an interior point. Right? So I need to show that if I pick a point in this open disk, it's necessarily in S. If I can do that, I've then showed an arbitrary point inside this set is inside S, which shows that this disk is in fact a subset of S. It's a subset of S, which is what we want. Okay, so what does this mean by definition? That means the modulus of z minus z naught is less than r, right? And what does that tell me? That tells me that the square root of x minus x naught, quantity squared, plus y minus y naught, quantity squared, is less than what? Is less than r. Which is equal to x naught minus 2. All right, so what am I trying to show? What's my goal? Oh, by the way, sidebar, right? Z is equal to x plus iy. I'm using that notation. So what am I trying to show? What does it take for z to be an S? What do I need? I just need what?
You need to be a complex number where the real part
Yeah, but for this z, what do we need? I agree with you, but we specifically need x is greater than 2, right? Hmm. I mean, what we've written down is not wrong. I guess this is the time in class I get stuck. Let me draw a picture of what's going on. So this is not part of the proof, obviously. This is me forgetting the next step. And so here we go. We've got, here's my z naught, right? And I've got z somewhere in here, right? So hopefully, right? Hopefully it's there. I mean, hopefully the disk isn't over here, right? So maybe I should look at rats. I am stumped at the moment. This is not a hard problem, guys. Wait a minute, I'm not stumped. This is as far as we're going to get in class. There's a homework like this, so you guys get to finish it, right? But you see geometrically it's true, right? So if we home in on that, that should be the key to how to do this, right? All right, tell you what, this is what we're going to do. Rather than, I mean, I know it's fun to watch me suffer for the next 10 minutes as I bumble my way into figuring out how to do this, but what would be much better use of your time is for me to go on. What I'm missing here is actually pretty simple. It's just like adding 0 in some kind of simple way and using the triangle inequality, probably like that. So what's missing here is about like 5 minutes. So I'll come back and make like a little video solution for that, and that way I won't torpedo this lecture. Let's go on, okay? All right, so. Unless one of you guys knows how to do it right off the top of your head. Maybe?
That quantity under the square root will always be greater than or equal to if you just have x minus x squared.
So you're just like z minus z naught is greater than or equal to the absolute value of x minus x naught?
Yes.
Which is necessarily what?
Less than x naught minus 2.
This is less than x naught? Oh, you're saying this is less than x naught minus 2.
Yep.
Does everyone agree with this? This is exactly what I was missing, just that step. And so the secret sauce that Ben is working with, and these are like really, really profound inequalities. Like, watch this. This is like really hard. If you've got z equals to x plus iy, let me right over here. Generically speaking, if you've got z equals to x plus iy, right, then the absolute value of x is less than the modulus of z, and the absolute value of y is less than the modulus of z. Like, this is, I know it seems stupid, but that actually really, really matters for these kind of arguments. Yeah, exactly, because indeed, it is the triangle inequality for the real and imaginary part. But you see this? This is wonderful, because now we have what? We have, rewriting this a different way, x minus x naught is less than x naught minus 2, right? What?
But if, like, y or x are 0, wouldn't they be equal? The magnitude?
Thank you. Very good. That's a very math major kind of comment. You math major?
Yeah.
Okay, good.
I had the same question I had.
Okay. But then you should be a math major.
That's why I'm not playing.
Oh, well, I guess I'll be content with that. So anyway, the point here is, now this is strict. Why? because it's not based on what you guys were just telling me about. It's based on this strict inequality right here, right? So I'm using the transitive property of inequalities to rewrite that, which then, going back to my college algebra, is we can unwrap like so, right? If you've got a real inequality, you can unfold it as this following compound inequality, right? And then what do? You add x naught across this, right? So adding x naught across this gives me 2 is less than x is less than, apparently, 2x naught minus 2. Now, right? So this, which of course implies that x is less than 2, thus, so x plus iy equals to z is an element of S, which then tells me what? That tells me that our disk of radius, I've called it R, centered at z naught, is in fact a subset of S.
Because every point within there also satisfies the condition for it to be S.
Right, because the z we picked was arbitrary. So it's good for every point. Therefore, z naught is an interior point, but interior point, hence S open as z naught was arbitrary, right? So sorry I faltered there in the middle, but thank you to Ben for the save. I do appreciate it. Saved me making a video. Woohoo! Yes, sir.
Just visualizing that with the R that we picked for the circle, then it is the circle we were testing on, then tangent to that x equals 2, is that correct?
Tangent, what are you talking about tangent?
I'm just trying to visualize what we did. With the R equals x naught minus 2, we were practically testing with a
Oh.
open.
Well, I mean, geometrically speaking, when you look at the disk, like this would be the closest point, right? So if you know this is at 2, right? X equals to 2. So if you take x naught minus 2, that's like the distance from the center point to the fuzzy edge. So as long as we make that our radius, we can't get over the fuzzy edge.
Right. We were testing with being right on the edge, though.
That's true. Yeah.
His point being we were being greedy about it and thus
You-
using an oscillating
You could, of course, take this radius and divide by 2 and not be so close to being wrong. Yeah, but, you know, we don't have to. All right, so that's how to work a problem like this. I think I might have given you a similar problem in the homework, but like for a half plane in the vertical sense. But if you understand the argument here, you ought to be able to like modify it for there. There's a more fussy question in the homework where I ask you to prove that an open disk is open. What does that mean? How would you prove an open disk is open?
Can you take an arbitrary point in the open disk and then draw a smaller open disk around said arbitrary point?
Well, that's the question, isn't it?
I mean, so long as you can draw an open disk, we don't exactly.
Well,
care.
let's
The disk itself is
think about this open disk here for a second. I'll help you out with your homework a little bit. So this is Z naught, right? And let's suppose this right here is the halfway point. Something magical happens at like R over 2 versus R. That was supposed to be halfway. You get the idea. Oh well, my bad. I will just tell you this. You need to think about two different cases, right? If you're picking the point that you're trying to prove the point is interior, if you're trying to prove like this point, you know, let's call it Z1. If you're trying to prove that point's interior, then you need to be able to find a radius, right? Like such that d R1 of Z1 is a subset of the disk of radius R centered at Z0, right? You're going to have to look at that. But the radius you're going to want to use there is going to be different than the radius you're going to want to use for a point out here, like let's say Z2. I believe, if I remember the proof correctly, there you kind of like need to think about these two different cases. Anyway, listen, let me not say too much about it. You can think about it. It's not as easy as that one. It does require some kind of thinking. You got to think about, how can I fit a ball inside the ball such that I'm not outside, right? And then it's like triangle inequalities and the things we've been looking at. But I don't think that one's not about this real imaginary part. It's about triangle inequality. All right, enough about that. What else should I tell you about? Well, why are they so giggly over there? What's something that must be very exciting. All right. Let's see where I am. Cool. So theorem. Did you got me over here? Okay, cool. Thank you. I do appreciate it. So one thing I should mention is there's one nice theorem. If U and V are open, then U union V and U intersect V are also open. All right. So I have the proof in the notes that the intersection is open, and like the way to do that, I'll just like draw some pictures to show you how that goes. So if this is U, right? And this is V. Oops. U, V. Suppose they're both open, right? First of all, if they don't intersect at all, if you sort through our definitions, the empty set is open. It's kind of tautologically true because there's no point. It's just trivially true. Like the empty set is by definition open. So let's suppose that there is a point of intersection, all right? If there is a point of intersection, say Z naught, what does that mean? That means that Z naught is an interior point to what? To both of them, right? Yeah, so on the one hand, I have some open disk of, say, radius R, let's say V. On the other hand, I have an open disk of radius, let me use the red, of the radius for the U set, right? Because it's an open disk in both respects. So maybe that's radius U. So, my bad, I should have, let me make this not work out so nicely. Let me, it's too late. I mean, in principle, both of these sets don't have to fit inside the intersection, right? Like it could be so that one of the disks, one of the open sets I pick goes outside of the intersection, right? But the other one doesn't. Let's see if I could achieve that. If I just made this purple line go a little bit more like here-ish, something like that. So like part of the part of the RU disk is outside of V. All right, that could happen. My picture's not awesome. My point to you is simply this: how would you pick? What radius would you pick to prove that Z naught's interior? Well, you just notice that if we let R equal to the minimum of the radius, right? Then you can easily see that the disk of radius R centered at Z naught is a subset of U intersect V, right? Because it's a subset of both. Therefore, what? Therefore, this point is an interior point, right? So that proves then that an arbitrary point in the intersection is interior. Therefore, the intersection of two sets is open, if they're both open. All right? This hinges strongly on there being just two sets, right? You could extend this to n sets, but if you tried to do this for an infinite collection of sets, it fails. Because you're picking a minimum. You can't pick a minimum from an infinite list. You can pick a minimum from a finite list, which means this proof generalizes to a finite collection of open sets. The intersection of finitely many open sets is open. The closed, the union is even easier, right? The union argument's just stupid. If you look at the union of u and v, pick a point in there, z naught, right? Well, then z naught's either in u or it's in v, right? It could be in both, but whichever. If it's in u, then there's an open disk around it inside u, right?
Guaranteed.
And if it's inside u intersect v, so it's interior. Like the proof that the union of open sets is open is just dumb in this context. And that applies if you can take the union of infinitely many open sets and still open. This theorem actually becomes the definition for topology when you take the course. By definition, a topology is a collection of subsets such that the finite intersection of open sets is open, and the arbitrary union of open sets is open. And then the third axiom is that the whole set and the empty set are both open. Those three things taken together define a topology. A topology is like a subset of the power set. It's a collection of all sets which we declare open. But the topology we work with in complex is a metric topology. It's a topology based on distance. So we can think about boundary, we can think about open and closed in the same way we're thinking about it in calculus. We talked about open and closed in calculus here and there, right? In calculus 3, just come up here and there. If you look at the theorems, the statement of the theorems, it had to be there if they're being careful. They might not have. I know I'm not careful sometimes. What else should I tell you about? What do we mean if we say a set is bounded? Is this set bounded? Yes. Why is that? Simply this. I can find another color marker, like this green, and if I can do it, let's say that point is big Z, there. See the big disk centered at Z? It contains everything in S. Therefore, S is bounded. To say a set is bounded in the complex plane just means you can find a sufficiently large disk that you fit your whole set inside. It's just a fancy way of saying the set is finite. It doesn't go on forever, all right? A set which is closed and bounded is said to be compact. A compact set is both closed and bounded. Compactness is important because we have really nice theorems about compact sets, like the continuous image of a compact set is bounded. In Calculus 1, you saw this as the extreme value theorem. But its more general statement is what I just said, that the continuous image of a compact set is bounded. All right. Let us move on. Yep.
So you have a set that is closed but not...
Closed but not bounded? Absolutely.
Would it be like if we had greater than or equal to x equals 2 or something like that?
That would work. Yeah, greater than or equal to 2 would be closed. True. It would contain its boundary. Its boundary is the line x equals 2. X equals 2 is the boundary line, is the boundary of the set. The whole complex plane is closed. The whole complex plane is open. Why is that? Because as a whole, the complex plane, what's the complement of the complex plane? Empty set, which is open. Therefore, the complex plane is closed. But on the other hand, you pick any point in the complex plane, you can find an open disk around it, so it's open. See, the complex plane is both open and closed. The empty set is also both open and closed. Those are the only sets which are both open and closed in the complex plane, I believe. Yeah. All right. In the standard metric topology, of course. Yep. Do you guys know what the power set is?
Set containing all subsets?
Yeah, the set containing all subsets. You can use the power set to define a topology on a set. If you do that, what you're saying is that every single possible subset is open, which means that every single possible subset is also closed. because its complement is a set which is open. That means that every singleton is both open and closed. Like this is called the discrete topology. It's just kind of dumb. I don't know, but what's that?
The finest topology.
The finest topology. It's like, you need to get me, should like serve it on rocks or something. I don't know. Let's see here. Oh, I'm sorry. You're Baptist. We don't do that. Let's see here. Wait a minute. No, we're non-denominational. We can drink if we want. Wait a minute. I can't decide. Oh, we're Baptist? No, okay. We're Reformed Baptist. We can drink certain things. No. I think Reformed Baptists can drink whatever they want. All right. All right, let me stop my meaningless banter and go on to actual math. So what I'm showing you right now, roughly speaking, is just geometric topology. And so for the most part in here, we use it descriptively. We don't really fuss too much about it, but it doesn't matter. It does matter. The other thing that matters a lot is connectedness. So if we have, let's say, A to B. Now you thought that was the interval from A to B. I got news for you. This is the directed line segment from A to B. So this is A plus T times B minus A, such that T is an element of 0 to 1. So this right here, my friends, is, if this was 1 plus I, and over here you had, I don't know, 8 plus 2I, all right? This directed line segment right here would be 1 plus I, comma, 8 plus 2I. It's that set of points in the complex plane, right? So that's pretty neat. It's a nice notation. Definition: a polygonal path. Polygonal path, or broken line segment, or whatever you just said. Looks like this. So you start with, let's say P, and then Z1, and then Z2, and then Z3, and then Z4, and you get the idea. Dot, 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 dot. Eventually we get to Zn minus 1, and then let's say Q equal to Zn. So the polygonal path, or polygonal path, if you like. If you want to say it like not like a savage, like me. Let's see here. So P to Z1, union Z1 to Z2, union da da da, union Zn minus 1 to Q. So this is the polygonal, or excuse me, polygonal path from. Now you got me self-conscious about it. Thanks a lot. From P to Q, right? Yeah? All right. Definition: S, a subset of the complex numbers, is connected if for any, let's say P comma Q and S, there exists a polygonal path. I learn, right? Gamma from P to Q, where gamma is a subset of S, if you'll understand my meaning. All right. Yes, sir.
So for when you have A to B, that's like complex, and then when you have 0 to 1, that's real. It's
Yeah.
identical
What's
notation, but they need different things.
Well, yeah, context.
I don't like the connotation.
If this is troublesome, we could replace it with this. Or if this is bothering you. There you go. Of course, this, context here is, of course, let A and B be complex numbers, right? All right, fine. Now, all right, so that's a connected set. So this is, if you had topology, you'd recognize this as path connected, kind of, right? A path is just a continuous mapping from, a connected subset of the reals to your topological space, let's say. So this is more technical than that. It's a broken line segment, but yeah. Now, if we have an open connected set, what's that? An open connected set is a domain. All right? A region is a domain together with some or all of its boundary. I'll get out of the way here in a second. So yeah, a domain is an open connected set. Let me, a little bit more to talk about here. A what?
If you have a connected set, it must be one of those two?
If you have a connected set, a connected set doesn't have to be open. It doesn't have to be a region. You could have a connected set which is not open nor a region. For example, well, like I don't believe that non-empty domain. There we go, non-empty. Maybe that'll fix whatever you're trying to do to me. Because the thing is this, like if you want me to, you could do some kind of wackadoodle thing like this, I think. These are supposed to all be line segments, right? Just that. Would that be connected? It would, because you can follow line segments to get between any two pair of points. Is it open? Is a curve open or closed? What if you just have a curve? Like and when I say a curve, I mean the set of points which it covers, right? Not, is this, if I take this path here, is this open or closed?
Are the endpoints of the set?
There you go. I'll include that one and exclude that one. Yep.
Don't we consider it closed from one side and open from the other?
I'm talking about closed and open as we've defined it today in terms of complex plane. No, a curve would be a closed set because I think it would be, well, oh man, rats, thank you. Phooey. I better include the endpoints, otherwise I was about to get logically stuck. Complement that. It's everything with just this little sliver of the complex plane missing, right? So you can draw an open disk around any point. That makes the complement of this open, therefore a closed curve is indeed, a curve with its endpoint is closed. Or if the curve went on and on forever, also would be closed, right? This is closed, so it's equal to its boundary, right? If I'm not including the inside here. I'm just including the marker to be clear, okay? Not the inside, just the edge. No inside, empty. All right. If I'm including the inside, I'll try to shade, guys, okay? Just as a point of communication here. So we want a region to be something that's like, it could be like, the thing I had on the board and erased earlier would be a region. All right, this would be an example of a region. Because it's connected, right? So in other words, and it would be open if you got rid of the boundary, right? If you made the whole edge fuzzy, it would be an open set. But you got some boundary points, so it's not, it's not an open set. But that's a region. A region means that it's something like that. A region is often what you want to actually do a calculation over, something like that. So region and domain is important to us. Yet another terminology besides connected is star-centered. What do we mean by star-centered? So something is star-centered if it, looks kind of like a star. I mean, that'll do it. The point with a star-centered thing is there's a center point called the star. I'll call it Z star for lack of imagination. And if you go from that, you see what happens? You can get to every other point in the set from line segments that begin at the star center and go on out, right? So if you can find if there exists a star center, then the set is said to be star-centered, right? That's a star-centered set. Is this star-centered? So proving something's not star-centered, like really proving it, is kind of obnoxious, but you can kind of see that it's not, right? Because if you try to put the star center over here, well, fine, you've got, you got a lot of it, right? But, maybe you're missing this part right here, right? So maybe you move the star over here, then you get that, right? But I think if you just look at it, you're always going to be missing, like maybe this piece right here is going to be missed. There's no place where you can pick one star and get to all of this set all at once. Here, let me make something easier for you to see. A slit complex plane. So you throw this out, right? Everything else is in except for this. This is the negative real axis. All right. So this is called C minus, the slit complex plane. I also define a C alpha, which is like everything in the complex plane except for the ray at angle alpha, right? So we could define a slit complex plane where we just throw out one angle, one ray. This is the kind of set we want to work on if we want to make our choice of angle continuous, if we don't want to let it have a jump. If you don't want to let the angle jump, remove the place where your argument jumps. Voila, continuous. So removing this makes the principal argument continuous. I keep using that word. What does it mean, continuous, right? We'll answer that shortly. You guys tell me, where's the star center for here? Could it be down here? No, right? Can't be down here. Because if it's down here, you have to go outside the set. You can't get through here to get up here. You have to put the star center like over here. But if you put it over there, you can get to every other point in the slit complex plane by taking a sufficiently shallow. You got to remember, this is just my picture. It's actually a line, right? It has no extent. So by taking a shallow enough line, you can hit points arbitrarily close to the negative z-axis. And this is not unique. You could choose any point on the positive real axis to be a star center for this. Yes, sir?
Is there any significance to, what is it called, a region where every point is a star center?
What does it mean if every point in the region is a star center? I think that makes the set convex. Yeah, that's a convex set. A convex set is one for which the line segment between